Welcome to Crops TV. I'm Melissa Miller. I'm the project director for the Iowa Nitrogen Initiative. We're here today to talk about the 2023 results of the Nitrogen Initiative on-farm nitrogen rate trials, talk a little bit about the modeling that will go into our decision support tool that will come out later this year, and then talk about recruitment because we're still looking for farmers to participate in our 2024 trials. About a year ago, we sat down with a group of farmers and a group of crop advisors, and we looked at what goes into making decisions about how much and when and where to apply nitrogen in any given year. When we looked at this, we talked about not just what resources we use to make those decisions, all of the different factors that go into it, but also even some of the emotions that we feel along this way. Being anxious or uncertain, that's something we have in common both when we talk to our farmers and our farmer advisors. Being excited when we finally see that corn plant popping through the ground, relief once we've harvested and we've seen our yields for the year. And so as we move through this process, we ask ourselves, what can we do to put good science behind the tools that we provide to farmers and their advisors to make nitrogen rate decisions that will improve profitability and environmental performance of their cropping operations? So the Iowa Nitrogen Initiative, hundreds of on-farm nitrogen rate trials every year. This is a public-private partnership between Iowa State University and private farm fields across Iowa. What we do is we look at the historical yield of a field. We find a 5 to 10 acre area of that field in which to conduct a trial. We choose, along with the farmer, 5 different nitrogen rates to test. We write a variable rate prescription that has those 5 rates in 5 different times. We give the prescription to the farmer or their applicator. They make the application in the spring or in the fall, whenever they do their normal nitrogen application. And then we get from the farmer the as-applied data, and then in the fall, the harvest data. The only variables that we alter are the nitrogen rates. Everything else is farmed as usual. And what do we get from this? A massive data set that we can use to dive in to understand why optimum nitrogen rates vary and predict optimum nitrogen rates for the future for better decision making. But why are we so focused on nitrogen? I'm going to pass this off to Professor Mike Castellano, who is the co-director of the Iowa Nitrogen Initiative, to talk a little bit about what we know about the science behind nitrogen and how we can make our nitrogen rate decision making better.
Thanks, Melissa. So why focus on nitrogen? Why the need now to update nitrogen information for better decision making in the state? So I want to highlight a few things here. I realize this figure is a little bit complex, but I want to walk you through it slowly. So the top panel here, we're looking at corn following corn, and the bottom panel, corn following soybeans. On the y-axis, we're looking at the optimum nitrogen rate for production in those systems from 2000 to 2016. We have those 2 different systems, corn following corn and corn following soybeans, because those are the 2 cropping systems that the university makes nitrogen fertilizer recommendations for. At present, we make fertilizer recommendations for corn following corn and corn following soybeans in southeast Iowa, and corn following corn and corn following soybeans in the rest of the state. So back to the figure. Within that figure, we see those rectangle boxes. The blue ones, those represent the economic optimum nitrogen rate, and the red boxes represent the agronomic optimum nitrogen rate. What's the difference between those two? The agronomic optimum nitrogen rate is the nitrogen rate at which the next pound of nitrogen no longer increases grain yield. In contrast, the economic optimum nitrogen rate is the nitrogen rate where the next pound of nitrogen will increase grain yield, but not enough to pay for itself. And of course, that depends on both the price of nitrogen fertilizer and the price of grain. The economic optimum nitrogen rate always produces a yield that's 96 to 99% of the yield that is achieved at the agronomic optimum nitrogen rate. However, sometimes it can take 50, 100, even 150 pounds more nitrogen to get to the agronomic optimum nitrogen rate. So that's definitely not a target in most systems. So these blue boxes and the red boxes, the box represents the 75th and the 25th percentiles of roughly a dozen nitrogen fertilizer rates trials in the state of Iowa for that year. The whiskers, they represent the first and the 99th percentile of the optimum nitrogen rate for those trials. So if we just focus on the lower left box and corn following soybeans, the blue one there, the economic optimum nitrogen rate in the year 2000, we can see it varied from roughly 250 pounds of nitrogen per acre to below 50. So the first thing I want you to notice in this slide is that the optimum nitrogen rate is extremely variable across sites within years. You can also see that it's extremely variable across years. So just the next year in 2001, that same blue box, it ranges only from about 175 to a little under 100 pounds per acre per year. So much lower in the following year. The second thing I'd like you to notice on this slide is that over time, optimum nitrogen rates are going up. So think about that for a minute. Why are optimum nitrogen rates going up over time? There are three reasons. The first reason is that yield's going up over time. So as we harvest more nitrogen from the cropping system, we need to return more nitrogen in fertilizer. The second reason is indirectly related to yield. So as yield has gone up over time, what else has gone up over time? In other words, how have we increased corn yields over time? Think about that for a minute. How much bigger has the average ear of corn gotten over time? Well, the answer is it hasn't gotten any bigger over time, right? We have increased grain yields by increasing plant population. We have not changed the harvest index, the proportion of the crop that's in grain versus the rest of the plant, the stover. As a result, as yields have gone up, the stover production has gone up over time as well. What does that do, and why does it increase the optimum nitrogen rate? Well, it increases the optimum nitrogen rate because it keeps the soil cold, it keeps the soil wet. The high carbon to nitrogen ratio of that material, when nitrogen does mineralize in the soil, microbes suck it up quickly so that they can eat that crop residue. As a result, as crop residue inputs go up, optimum nitrogen rates go up as well. The third reason, which accounts for a lot less of the variability or the increase in nitrogen rates over time, is that growing season precipitation is also going up over time, and that leads to some more losses. One final point I want to make is that although the optimum nitrogen rate is going up over time, the nitrogen use efficiency of our cropping systems is also going up because the nitrogen harvested in grain is going up faster than the nitrogen we're putting in fertilizer. Okay, so current nitrogen fertilizer recommendations. How do we do this in Iowa? What we do is we go out and we do nitrogen fertilizer rate trials, just like you can see in the background of the slide there. But in the past, we've done them in replicated plots on research farms, and maybe we do about a dozen in a year. And what we do is we take that optimum nitrogen rate from that trial and we plot it on a figure like this, where each one of those points represents the optimum outcome of one nitrogen fertilizer rate trial in one location in 1 year. So together we have about 150 trials on this figure from different locations in different years. And what you notice is that there's not a big pattern between the optimum nitrogen fertilizer rate on the x-axis and the grain yield we get at that optimum fertilizer rate for economics. And so, as a result, at the university, we basically just recommend roughly the average. It's a little bit more complex than that, but for all intents and purposes, you can think about that as the average, and that's represented by the star there. So the point I want to make here is that if everybody applies the university nitrogen fertilizer rate recommendation, and this happens to be corn following soybeans in the main part of Iowa, roughly a third of farms will over-apply nitrogen, a third will under-apply nitrogen, and the remaining 40% will apply just about the right amount of nitrogen. So the point here is that there is significant opportunity for improvement in nitrogen fertilizer information for decision making in the state. There's also, as we make those improvements, real opportunity for environmental benefits, improvements in environmental outcomes from nitrogen fertilizer management. So on the previous slide, we were looking at those optimum nitrogen rates as a function of how much nitrogen we're putting in. Here, the x-axis now is relative to the optimum rate. So we're showing you how each one of those trials, represented by one of those points, would turn out if everybody applied the university recommendation. So if everybody applied the university recommendation, again, about a third would be applying too little nitrogen, about a third would be applying too much nitrogen, and about 40% roughly the right amount of nitrogen. By getting everybody to the real optimum nitrogen level for their farm, we're talking about personalized nitrogen management here as a function of location, management type, weather year, will actually reduce environmental nitrogen losses because although we'll be bringing about a third of fields up in terms of the amount of nitrogen they're applying, that extra nitrogen is going to lead to very little environmental loss because there's a place for that nitrogen to go in the plant in increased production. In contrast, by bringing the third of people that would be over-applying if they followed the university recommendation down to the optimum, shown in the green there, will make significant reductions in environmental nitrogen losses because those extra nitrogen inputs, they had nowhere to go. There's no sink for them in the crop, and as a result, the only other place they can go is the environment. Optimum nitrogen inputs also super important for soil health. This is some work summarized from my colleague Sotirios Archantoulis, who will speak in a few minutes, and my group here at Iowa State, showing that the optimum nitrogen fertilizer input is critical for maximizing soil organic matter and soil carbon stocks, which we often use as a proxy for soil health. So you can think about this as getting the right amount of nitrogen is important for maximizing soil health outcomes. If we apply too little nitrogen, we have lower soil carbon stocks. Why? Well, because we're not producing that residue that we talked about earlier, which is a critical input for maintaining and growing our soil organic matter basis. Alternatively, on the right side, if we over-apply nitrogen fertilizer, why might we have less than maximum soil carbon, soil organic matter stocks? This took us a while to figure out. A lot of folks have talked about how excess nitrogen might burn soil organic matter by promoting microbial mineralization of it. We found that not to be the case, in fact. What we did find out, however, which we'll follow up on in a minute, is that excessive nitrogen consistently reduces corn root production. Consistently reduces corn root production, and roots are a disproportionately large contributor to soil organic matter. As a result, we have a little bit lower soil carbon and soil organic matter levels when we over-apply fertilizer. And as we'll discuss in a minute here, that excessive nitrogen can also reduce yield in some cases, about 15 to 20% of the time. So, thinking about that, let's turn to the 2023 crop year trial results from the trials Melissa talked about. Here is a map of the trials we had out in 2023, 270 on-farm trials, 148 fields. Some of those trials were split in the high-yielding part of the field, the low-yielding part of the field, with 72 farmers. Here are just the results. You can see that there's a variety of yield responses to nitrogen fertilizer rate. A little bit about the trial characteristics. On the x-axis there is just simply the count of the trials. You can see that urea AMS blend was the most common fertilizer source. Ammonia was the second most common, and then so on and so forth. Here, looking at the economic optimum nitrogen rates and the yield outcomes from the trial. So on the left, we're looking at a figure just like we showed before, the economic optimum nitrogen rate and the yield achieved at that economic optimum nitrogen rate. So here we can see a little bit more of a positive pattern, but again, it's quite a scatter plot. Clearly, knowing the yield is not an accurate predictor of how much nitrogen is required to achieve that yield. On the right panel here, each one of those red bars represents a unique farm, a unique trial on that farm, and you can see that the optimum nitrogen rate varied from a minimum of 77 pounds of nitrogen per acre to a maximum of 353 pounds of nitrogen per acre. So one of the things we're really trying to answer with the Iowa Nitrogen Initiative is, how can we move folks over from high nitrogen rates and low yields to low nitrogen rates, sustainably low nitrogen rates, that is, and high yields? Nobody wants to be applying 300 pounds of nitrogen fertilizer to achieve 200 bushels per acre. We'd much rather be applying 200 pounds of nitrogen to be achieving 250 bushels per acre of production, a much more efficient outcome. Here are some examples of trials from the same multiple fields across the same operation. We can see that the yield responses differ here. We can even see in the top row there a trial where excessive nitrogen, in fact, did reduce yield, as we've observed in about 15 to 20% of our trials. The main thing I want to emphasize here, though, is that the outcomes vary enormously, even within the same operation across fields. Again, getting to the importance about really understanding how management factors, soil types, plant populations, and genetics, how all those things affect the optimum nitrogen rate. Here in particular, we see a few trials where we had those negative outcomes associated with excessive nitrogen fertilizer application, or fertilizer application above the optimum. What might be going on there? Well, we talked about earlier how we know that too much nitrogen fertilizer reduces root biomass consistently. Our working hypothesis that we're trying to test with the Iowa Nitrogen Initiative, and to better understand how that excessive nitrogen reduces corn yields, we think that the excessive nitrogen reduces corn yields in years where the corn experiences late season stresses. It might be drought stress, it might be a pest, it might be wind. But we think that that's what happens when the over-application of nitrogen for that specific operation is paired with a late season stress. We experience the yield loss. And again, we observe that in about 15 to 20% of trials. Did sidedress pay in a year like 2023? About 45% of our trials, the answer was no. And about 55%, the answer was yes. Again, just highlighting here that we really need more information to help guide sidedress fertilizer application. When do we need it? When do we not need it? How we can switch from pre-plant to in-season sidedress application and be more confident about the amount of nitrogen that we need with that sidedress application. All questions we're working on with the Iowa Nitrogen Initiative. And finally, nitrogen use efficiency. So the pounds of nitrogen per bushel in our 2023 trials. Here you can see it varied from a minimum of 0.38 to a maximum of 1.47 pounds of nitrogen per bushel of corn. On the right there, we're looking at each one of those yellow bars represents an individual trial. The upper dotted line represents the old historical yield goal recommendation of 1.2 pounds of nitrogen per bushel corn. You can see that there really is no reason to be up that high anymore. The greater efficiencies are easily achievable, much lower than that. And then that lower dotted red line, what we're showing there is 0.55 pounds of nitrogen per bushel. That is the lower limit of what sustained nitrogen use efficiency can approach, because a bushel of corn has 0.55 pounds of nitrogen in it. So we can't be fertilizing less than that, or that means we're mining our soil organic matter. That nitrogen has to come from somewhere, and over the long term, it's unsustainable. It may be sustainable in a really good year or two when we get a lot of nitrogen mineralization from the soil. There's no reason we shouldn't take advantage of that. But again, sustained year over year nitrogen use efficiencies really below probably 0.6 pounds of nitrogen per bushel, accounting for some environmental losses, which will always happen in corn and soybean systems and natural unmanaged systems as well. We have to account for those, and we couldn't be below that for the long term in a sustainable fashion. So with that, I'm going to pass it over to Sotirios Arkantoulis, who's taking these data and putting them into cropping systems models to better understand, predict, and forecast optimum nitrogen rates.
Thanks, Mike. I'm gonna provide you some more information about the modeling and what we are going to do with the Agricultural Production System Simulator in the Iowa Nitrogen Initiative. Before I go into the details, I want to provide some comments about the use of modeling. It is a perfect tool to get more value out of the data, and it is something that is used for many, many years in climatology. However, this is not as common yet in crop science and soil science. We are getting there, and we are going to leverage more this project to make the models better and get more out of this. Now, regarding the APSI model, the model that we are going to use in the Iowa Nitrogen Initiative, it is a process-based, it is a science-based model. It is driven by equations developed over many years through PhD programs and MSc programs. The APSI model is the most used cropping system model in the world, and one reason that makes it one of the most used is that it is updated almost every week. So the most recent science-based information is getting into the model. At Iowa State University, we are working with the APSI model. We are improving the APSI model over the last 6 years. And Iowa State University is the USA hub when it comes to model improvement and development. We are using the model for research, extension, and teaching. And the model, it's complex. It accounts for many different crop models, soil models, and it requires many inputs. And I will provide you an example of the inputs later on. But if I am to categorize the inputs, we need soil information, we need management information, we need cultivar characteristics, and we need weather. I know it sounds a lot, but the model also offers a lot. It can provide information for over 100 variables, including crop yields, NTO emissions, nitrogen leaching, and many others. The model can also simulate crop rotations, cover crops, and many different aspects of the cropping system. I will provide you a simple example of how the model inputs look like and what we get out of the model. On the left side of this slide, you can see model inputs, which includes the planting date. We need to know something about the cultivar. Is this a long maturity? Is this a short maturity? We need to have an information about the plant population. And Mike mentioned before how important was that for the yield increases. We need to know the row spacing. And then we need to know what is added to the field, like nitrogen fertilizer. And when was that applied? This is very, very important information. And then the previous crop, whether the field has any tillage or is without any tillage, and then some other information that I have there about subsurface drainage and manure. Usually, we tend to ignore this type of information, but it's really important when it comes to cropping system modeling, because both subsurface drainage and manure can change the nitrogen dynamics in the soil by a lot, both magnitude and direction of flows. And of course, to simulate a cropping year, we need to know the location and we need to have the weather data. And in this particular example, I have Central Iowa and the year 2019. Giving these inputs, the model is going to give us some outputs. And a little summary of the outputs is the grain yield, 237 bushels per acre, the nitrogen that is exported during harvest together with the grain, 140 pounds of nitrogen per acre. We can see how much is left behind, the stover nitrogen, how much is in the soil, in the topsoil, how much has been leached, and many more information from the model. Now, any change we do on the left side of this slide, any change in the input is gonna change the outputs. So it's very important to get metadata and as precise management information as possible into the model. When it comes to nitrogen recommendation, the way that we are using the APSI model to simulate the yield response to nitrogen is to run the model for many different nitrogen fertilizer rates. So we can reconstruct the yield response to nitrogen and then by fitting a statistical model to get the optimum nitrogen requirement, which is extremely important to get as close as possible to the optimum nitrogen rate. Now, the model can give us more than end-of-season information. Here I provide an example of additional data that we can see through the model and understand what went well in the system and what went wrong in the system and what we can improve. The model can give us data every single day. And in this graph, I provide you some information about the soil nitrate. The orange line in this panel represents the soil nitrate fluctuation day by day in the top foot, and the blue line, the soil nitrate dynamics in the second foot. And the black line is how much of this nitrogen is accumulated into the plant, the whole plant, the crop and uptake. And there is a bar there that indicates the date and the amount of nitrogen fertilizer. Through experimentation, we try to collect data to make sure that the model provides the right answer for the right reason. It is quite often in modeling to get the right answer for the wrong reason. We want to achieve both. And to ensure that, we pay attention and our experimental frameworks account for initial measurements of the soil nitrate. It is very important to have a good sense what is the starting point, and also the second most important measurement that we're going to extract through experimentation is how much is accumulated in the plant and how much of this is exported. And this is how we check that the model performs well. Over the years, we have done enough testing, but we don't stop over there. We continue testing the model because the agronomic system is quite dynamic and changes every year. As the hybrid changes, as the soybean varieties changes, the weather, everything, we need to keep updating the model. Here I provide an example of a study which was published in year 2020, and in this study we tested and we improved the upstream cropping system model across 7 locations in Iowa. It was a 5-6 year study, and we studied corn, soybean systems with different planting dates, management practices, and I provide some example here, measured versus simulated data. In this particular example is the soil nitrate. This is one study. The most recent study that we published was about the crop yields and the optimum nitrogen fertilizer. In this study, we tested the APSI model over 20 years of experimental data, covering 14 locations in Iowa and Illinois, and there was a total of 386 nitrogen trials. We tested the model in simulated corn yield response to nitrogen, the optimum nitrogen rate under 2 different crop rotations. The model performed well, was able to replicate the dynamics, the low and the high yields, the low and the high optimum nitrogen rate. But as I mentioned before, testing and improvement of the model is not stopping. We should not stop. We should take care of the models. And here I will provide the analogy that simulation models are like cars. If you leave your car without maintenance, without everything, the car is gonna leave you. And the same applies for the models. We have to take good care of the models. We have to maintain. We have to add new science advances so we improve accuracy and we decrease the error that comes out of the model. And it is very important, like the cars, to provide good fuel into the simulation model. And when it comes to modeling, the good fuel translates to accurate metadata, correct weather information, soil profile characterization, and cultivar information. Everything gets down to we need data. This type of complicated models that can provide us lots of insight and predictability of the system have high input data requirements. And this is the importance of the Iowa Nitrogen Initiative and all the data that are going to be accumulated across the landscape. This is very important for modeling. Through the Iowa Nitrogen Initiative, we are going to develop web tools to help farmers make informed decisions to improve productivity, profitability, and environmental sustainability. We are going to use two different data sets. Both of them, they are going to get into the model. We are going to use the on-farm data that both Melissa and Mike mentioned before, and we are going to use some additional detailed experimental data where we were able to collect more information in season to improve the science behind the model. All of this data will enter into the model. Then we are going to use the mechanistic power of the model to expand the amount of data that we can simulate and create a very big database, which later are going to be used for statistical modeler, and they are going to be used by web developers to package it in a nice web-based tool. And I'm going to give you one example of what I mean by detailed experimental data and complicated experimental data I want to add to this one. This is one experiment. We call it 5 by 5 by 5. It had 5 nitrogen rates, 5 different plant densities, 5 different hybrids, 2 rotations. We ran these experiments over 4 or 5 years, and in total we accumulated 140 nitrogen trials. And the optimum nitrogen rate ranged from 30 to 300 pounds of nitrogen per acre. The reason why we ran this experiment was to understand the interactions. And the second reason was to check whether the model can predict all these type of interactions between density and hybrids and everything. If the model is able to replicate these complex experiments, our confidence in the model increases by a lot, and this is how we are going to use the model with robust data behind to develop the decision support tools. From this complex experiment, I'm going to show you one combination of factors where you see the grain yield responds to nitrogen rate by different plant densities. There are 3 different colors here. The points refer to observations and the lines to the simulations from the APSI model. There are 3 different plant densities, 14,000, 23,000, and 55,000 for one particular height, one hybrid, and one crop rotation. The model is able to replicate the observations pretty well, and you can see there is a trend that there is higher optimum nitrogen rate with increasing plant density. There is a small trend there. It's not large, big change from one plant density to the other, but there is this trend there. This is what we get out of the APSI model. And right now, in this particular data set, there are 2 postdocs and 1 programmer working to make sure that the model it is in a good shape and can replicate all this data. Following process-based modeling, we have to work with a statistical model to extract the most important information, which is the economic optimum nitrogen rate, the yield at the economic optimum nitrogen rate, and the nitrogen use efficiencies that Mike presented before me. And here is an example of a recent work that we did at Iowa State University, where we developed a new empirical statistical model to estimate the optimum nitrogen rate response to grain yield, which also accounts for different plant densities. This is something that we are gonna evolve through the Iowa Nitrogen Initiative and expand further, and we are gonna use it. I gave you a little taste of what the detailed experimental data looks like. Melissa and Mike provide you information about the on-farm data and then the statistical model. This is the framework that we are following and the work that we are doing in many different categories towards developing the final product, which final product is a web tool. And we plan, our goal is to develop a beta version in year 2024. And I provide here an example of how this is gonna look like. And I borrow the example of another web-based tool that we developed in year 2015, and this is the soybean planting decision tool, where on top we have different inputs for the user to select, like location, crop rotation, planting date, hybrid maturity, planting dates, soils, weather years, and the model is going to give information about the optimum nitrogen rate yield and is going to benchmark different production situations. It's going to be an educational tool, very informative, something that users can use it from any place and at any time and can explore all different combinations of experiments that would have been impossible through traditional experimentation. We don't stop only on this type of tools and that is going to help decision making through probabilistic estimations of optimum nitrogen rate. We plan to use the model to understand what happened in every growing season. And here I'm going to present one example, one what if model scenario example regarding the timing of nitrogen application. Very often I'm hearing that if I knew the weather, I can tell you what is going to be the nitrogen rate and what is the best time to apply the nitrogen rate. What I have here in this example, I have a chart, I have a graph of the precipitation, daily precipitation for the year 2023 for Central Iowa, where we planted a corn, 111-day corn, on May 10th. So the question that we had using this data is, when is the optimum, when was the best time to apply nitrogen, and what was the optimum at different nitrogen rates? You see here the distribution of different precipitation events, and then we start thinking about probably it was better after the rain, or it was before the rain to ensure that there is nitrogen across all the profile. This is something that the model can give us lots of insight and make us think more of the system and the interactions. Let me give you some data on this one. We ran one simulation experiment where we applied different nitrogen rates on April 1st. The optimum nitrogen rate, it was 190 pounds nitrogen per acre, and the yield was 100% of the potential yield. We repeated the simulation with an application timing of 1st of May. The economic optimum nitrogen rate decreased by 5 pounds. However, the yield, it was still 100% of the yield potential. The next run was the 1st of June. The optimum nitrogen rate was 180 pounds and the yield maintained at 100%. And through modeling, we can go to the extremes. We can go to experiments that farmers and many others will not run in the field because they are going to get a yield penalty. And this is the situation when we apply nitrogen fertilizer, different rates, on July 1st, a week before corn silking. And of course, through modeling, we don't have anything to lose, just a little bit of our time. We can go even further. We can go in the 1st of August and run a nitrogen experiment there. And the result in this case is that the optimum nitrogen rate is only 80 pounds nitrogen per acre. However, the yield is 70% of the yield potential. By looking all these different options, it is obvious that the June 1st application time was the best for this particular environment and situation. We got 180 optimum nitrogen rate and the yield was 100%. Now I'm sure you will be wondering, how about a split application? And we ran this scenario where we split the nitrogen 50% in 1st of April and the other 50% in the 1st of June. In that case, the economic optimum nitrogen rate was 182 and the yield was 100% of the yield potential. And using this example, you can see there is not just one perfect application, timing and rate. The timing and the rate changes. We have many different kind of optimum scenarios that we can explore, and this gives us enough flexibility to go around the nitrogen fertilizer. That was one example application that I wanted to share with you, what we can get out of the model. And to summarize the modeling slides, modeling is a powerful tool. We can see what happened in the past, what is going to happen in the future, and get lots of understanding where we are now and what we can change. Very important to that is to have good data getting into the model and to have data across geographies, across different soils, across different management practices to ensure that the model performs well, can simulate the data, increase our confidence in the use of model, and make the best decisions. And I will turn it over to Melissa to give us more information about how you can contribute to the Iowa Nitrogen Initiative with experimentation and more trials. Thank you.
All right. Thanks, Sotirios. By now, you probably understand how important it is for us to have these hundreds of on-farm trials every single year so we can get the data that we need to feed into AppSim to get the very best outputs. But if you need a little bit of persuasion, I want to talk to you about why we need our farmers to enroll in the trial. So our goal overall is to make nitrogen decision-making easier. And as Mike discussed, as Sotirios discussed, we need the data from your on-farm trials in order to make that happen. What will you get out of the trial? Well, you're going to get information about your own farm and how it performed in the year that we did the trial in. So, for example, all of the trials that we did in 2023, we're having meetings with those farmers now to look at what their optimum rate was, look at how the yield performed in response to that nitrogen rate, and talk through some of those management decisions that we saw and what changes we can make for future years to bring that optimum rate lower and how that compares to their peers. Additionally, on trials that include a true zero added nitrogen rate, so nothing applied at any point, we do some additional soil sampling so we can better understand the carrying capacity of the soil, the nitrogen that exists already in the soil. So I have here on the slide just a list of what we're doing and when we're doing it so you can get a good idea. So we'll start off with a general fertility sample at the beginning of the year, and we'll get that out to you. That's as a thank you for participating. We don't actually use that information in what we're doing. Then we're going to get 0 to 12 and 12 to 24 sample cores at pre-plant in about April, post-plant in June, and then again after harvest. And then for trials that are accessible for our samplers, we will come in at black layer and we'll get ear collection and we'll bring that back to our lab and we'll do additional sampling on that. So we do that on our zero rate trials. We also do that on trials that are going to tell us something different. So for example, this year we're going to be looking at different manure sources. So if we have someone who's using poultry litter in their manure program and their nutrient program, we're going to want to take a better look at that so we can understand how the poultry litter impacts that optimum nitrogen rate. So why not to enroll? We've been doing this now. Last year was our first full year, and this will be our second full year. And to get hundreds of trials, we need hundreds of farmers. And so we've had a lot of conversations with some people who maybe aren't interested in participating, or they're interested, but there's something holding them back. So I wanted to talk through some of those common concerns that we have and hopefully ease your mind a little bit on why they may be less of a concern than you think. So our first concern is that you'll lose yield on the insufficient nitrogen plots. I want to assure you that, first of all, these plots are small. So especially even if you have a zero rate trial, we're only talking about an acre of the field. So it's a very small amount. Not every plot sees a loss. That's what we're trying to find out, right? And it's going to depend on how you have managed the field in the past and on the weather year and all kinds of different factors. So our trials overall, all this year, all averaged, almost entirely, all averaged over 200 bushels per acre as a whole. So we weren't seeing huge losses. Also, if you do one of those zero rate trials, we expect a yield penalty, and so we'll give you $600 to help compensate for that loss. Another concern we have is about data privacy, and this is something we take very, very seriously. We are only receiving data within the trial. We work with a third party to write the prescription and to get the as-applied files and the yield files back, but the information that comes to us after that data has been cleaned up is only the data that exists within that 5 to 10 acre area. Additionally, any personal information we have is just for contact purposes, so we can communicate with you about the trial and about any of the extra sampling that we're going to do. We keep that separate from the data that we have. And at the end of the day, even if we weren't taking all those precautions, your personal information is protected by a legislative exemption. So even though we're a public university, personal identifying information is kept private. Another concern we have is that it's going to slow you down. We understand that it's busy from day to day. You sometimes don't even know what field you're going into until a couple hours before, and there's concern that maybe it'll slow you down. And really, we take the time to design the trial, to have those conversations about now, this time of year, before you're getting into the field. And so all you have to do is make sure that you upload that prescription into the monitor before you start that application. Now, that doesn't mean that if we don't make your prescription now, you're not able to participate, because we've written prescriptions the 2 days before an application. I've personally ran out a USB with a prescription to somebody right before they started a field. So we can do it up until the last minute, but it doesn't have to work like that, and it doesn't have to slow you down. Now, we need on these trials to work closely with farmers and their advisors. So if you are working with someone, whether you're an advisor working with a group of farmer customers to help them make their nitrogen decisions, or you're a farmer that's working with a retailer, maybe they're doing your custom application with the variable rate, it's great to have both people on board. And we understand why you might be hesitant to participate in a trial, especially if your job depends on you being right and protecting a relationship that you have with your farmer. So a couple of these concerns that we've seen when talking to folks is, one, I mentioned we're working with third-party companies to do the soil collection as well as writing the prescription, and there's concern that those companies are in it because they're planning on using this as for personal gain in order to gain more customers. And that's simply not what we've seen in the time that we're working. We trust our partners completely. But for us, you have to understand that ruining your relationship with your farmer or impacting it negatively in any way is not going to help us do the science that we need to do. These trials are that important, and we're here to protect that relationship that you have with your farmer. Our partners are only there to work with your farmer on executing those trials. So we are here to grow the relationship between you and your farmer and not impact it negatively. The second concern is maybe you'll look back and your previous nitrogen recommendation could be wrong. And who likes to be wrong? I certainly do not like being wrong. But the fact is, we're all wrong. Mike talked about this, and Sotirios talked about this. The science, it's not up to where it can be. We have a lot of room to grow. That's why this project exists. So you can be part of the solution, and then you can always just blame us if things go awry. So let's talk quickly about how the process works. So if you have someone who's interested in it or you're interested in it, the first thing to do is let us know. You can get in contact with me, and I will have a brief preliminary discussion with you to make sure that you have what it takes, the equipment necessary to execute a trial. So we're looking for a variable rate nitrogen application capability with the ability to upload a script. So we can't manually do these trials. We need to do it automatically with that prescription. We also need you to have a combine with a yield monitor that you're willing to calibrate before you go out in the field. So those are really the two things that we need to know. So the next step would be a trial design meeting. We want to talk with you about what fields you think you can use, what rates we think we might want to use. A lot of the times we'll start with a rate that the grower is already using, and we'll go out 30 to 60 pounds on either side of that until we have our 5 rates. We also look at yield history. We look at header width of your equipment, all of the things that go into making a prescription that is for your farm and will get the best trial out of it. We give that prescription to whomever is making the application. It gets applied. We get that as applied data back by August 15th. So we have a couple months buffer. So you're not hopping out of the tractor, downloading that, going to the office, sending it over to us. We have some time. You can wait until you're done with that field work in the summer. And then in the fall, you harvest, same deal. We ask for those yield maps back by December 15th. So we can get that data in, and then we can analyze it, and we can get you your end of year trial report, and we can start talking about what we learned and what we plan to do with that information in the future. So I get this question a lot. Do you need more trials? And the answer is yes. And unless you see me sending a bat signal in the air that says no more trials, please, the answer is yes. We need as many as we can get. We see with the trials that we write, about 80% of them get executed correctly. My goal for this upcoming year is 500 trials. I would love to exceed it. And all you have to do is to get started is to call or text me at the number you see on your screen, and we can have a conversation and get started. Thank you for joining us today on Crops TV. Signing off, I'm Melissa Miller with Iowa State University.